So let's keep talking about the discrete logarithm problem from last week. And I'm actually going to tie in a bunch of the other concepts we've been talking about lately and why they're really, really important. So I'm going to introduce two different ciphers. In cipher and a key exchange. And you'll see the names right now, the Pohlig-Hellman exponential cipher and the Diffie-Hellman key exchange. Hellman was a critical member of getting all of this cryptography. In fact, he won the Turing Award about a decade ago for all of the things that he's done. That's one of the most prestigious awards in computer science. Hellman, just so you know, he was actually one of the first real major members to push forward a bunch of cryptography ideas and actually is often called the author of public encryption keys. He's the idea of how we actually do a lot of modern cryptography. We talked about RSA. It turns out that I can't remember. My brain is now having a blank, but you will see as we come back to this, I'll tell you a little bit of history, but almost all of them are actually related to Hellman. And this one, by the way, Hellman, one of his colleagues that he also helped out when we get to the Diffie-Hellman was Merkle. And Merkle is another person who's actually responsible for hashing and creating the hashing algorithm that we use in modern today. All right, so let's talk about Pohlig-Hellman exponential cipher. So it turns out this is a cipher, but it's actually a symmetric cipher. So it's a symmetric key cipher. Namely, we're going to pick a couple things, and I'm going to highlight what I want you to notice about this. So first, we pick a prime number and a key. Now, by the way, I didn't note this, but we want a relatively large prime number, but it has to be kept secret. We also pick an encryption key E, which is some number between 1 and p minus 2. We don't want p minus 1 because that's actually problematic. But we're going to pick anything besides that. Then there's a decryption, which is E times D, which is congruent to 1 mod p minus 1. Wait. I'm going to call this out and explain why that is true. So, and what that really means. The encryption of plain text is simply we take our message M and we raise it to the E power mod P, and decrypt is we raise it to the D power, the decrypt mod P as well. So we're doing exponentiation. So let's talk about why the heck all of this works. And it goes back to actually some things that we talked about previously and why these are important. So, and then I'm going to give you an example about how this actually works. So if you look at this real quickly, what this really means is that my cipher, so remember M, let's take this last statement right here, M equals C to the D mod P. But that's the same thing as M to the E, because that's what C is, to the D mod P. All right, wait, but that is the same thing as M to the E D mod P. But this statement up here that ED is congruent to 1 mod P minus 1 is the same thing as saying that ED equals P minus 1 times some integer K. I don't know what it is, plus one more. Because remember, that's the definition of what modular arithmetic is. So this is actually equal to the same thing as M to the K times P minus 1 plus 1 mod P. Okay, so how does this work? All right, I'm gonna have to I'm trying to keep it on this page, so you're gonna excuse me while I kind of do some more writing up here towards the top. So, but that's the same thing, just using what you know about exponents. This is M to the K to the P minus 1 times M mod P. Because when we have the plus 1 in the exponent, that turns into multiplication. But this portion right here is same thing as M to the K to the P minus 1 times M mod P. And this is the catch that's right here. By Fermat's little theorem, any value raised to the p minus 1 mod p is congruent to 1 times m. Oh, so the whole idea here is that I have to be able to find essentially the inverse of E mod P minus 1. And we're doing that, and then we're going to use the Fermat's little theorem to actually kind of leverage that. Now, here's why this is actually, and it's also further going to use a bunch of the different things that we've already talked about. So I'm going to clear all that out. Again, we're going to need to find inverses. Well, the problem is it's finding an inverse of P minus 1. If P is any relatively large number, then P to the M P minus 1 is going to be an even. So all the prime numbers besides 2 are odd. So you take 1 away, it's going to be even, which means it's no longer prime. And the key part about that is that actually means we cannot use the Fermat's little theorem method of finding the inverse. We have to use the Euclidean algorithm, the extended Euclidean algorithm. This is why I wanted you to practice the extended Euclidean algorithm previously, to understand how to find inverses. Also, this is why I wanted you to do Fermat's little theorems to understand now we're going to use Fermat's little theorem to undo exponentiation. So also we're doing exponentiation, which means we want to do that binary expansion and exponentiation. So all those concepts that I've been doing the last couple of things is to get you to this point in time. Now, this is really, really important because the symmetric key method is going to be used. So let's kind of look at an example about how this works. So I'm going to pick P. I'm only going to do 181. Again, I'm going to do it relatively small, and E is 97. Now, here's my plain text. Now, notice my message is an array, a list. These are, in this case, between 0 and 26, so you could translate them into the letters, and this could be B. Let's see, this one would be E. I forget what 19 is, and we could translate the rest of this. It doesn't really matter. This idea we can translate into the blocks. Again, this is why I wanted to talk about blocks real quick. We need something, and this is where picking our appropriate thing is going to be critical. We could have broken this into blocks, and this could be block 1. In this case, it's blocks of size 1, but we can pick them blocks, and then I have to pick a P that is larger than that each block possibly could be. This is so that you can have a one-to-one function. Real quickly, as a note from last week, just to illustrate, let's say my blocks, here's all my possible block values. These are all my block values. I'm going to do some kind of encryption. My encryption is going to take it over to some new space. So it's going to encrypt, it's going to do some kind of math, and it's going to send it over here. So if I have a block value, we will call it B, and I send that value B over here to a new encrypted block E. I need to have some way to get back specifically to B. If the P I choose is too small, then when I come over here, there potentially could be two different blocks, let's call it A and B, that E can go back to. And if that happens, my encryption has failed. So we need a one-to-one, which means we need this encryption space. So our prime number, whatever we're working with, has to be bigger than all the possible block values, not just the ones I have, but all the possible ones. If you even limit it to just the ones that show up in your specific message, you're actually translating information then to your to someone else, and they can understand that. So again, we have blocks. We're trying to do this. All right, so how do we do this? Well, we then encrypt each and every single one of them by raising them to a power, mod 181. So 1 to the 97th power, that's pretty easy for any, I don't care what mod you're talking, that's easy. 4 to 97 is kind of hard. What you have to do is, and this is where it's useful, what is 97? So if I take 97 over here, 97, that is a base 10 number. This equals what? Base 2. And essentially what we're saying is, well, let's look at the powers of 2. 2 to the first, 2 to the 0 obviously is 1. This is 2. 2 to the second is 4. 2 to the third equals 8. 2 to the fourth equals, and I'm just breaking it down so you can kind of see this. 2 to the fourth is equal to 16. 2 to the fifth is equal to 32. 2 to the sixth is equal to 64. And 2 to the seventh is equal to 128. So 97, I can break that in. I need at least 8 spots because I'm gonna need at least 7 spots. But since I'm doing 97, it's gonna take 164. So I have 64. I can't add 32, so the next one would be a 0. There's no 32s. But 64 plus 16, so I'm going to use one of these and one of these. Those combine to give me 80. Okay, so now I have to come with 16 more. Actually, I take it back. I just realized I did an error. So I have a 64 and a 32. These two combine to give me 96. So I'd have a 1 here. And then I need nothing else until here. So that's going to be a 0, 0, 0, 0. I have 4 zeros. 1, 2, 3, 4, and then a 1. And this is my binary expansion. And when we do our binary expansion, again, we're doing the squaring process over and over again. So I'm just trying to illustrate this and reiterate. And when you do the translate between different bases, some of you asked that, the hard part is you pretty much have to go through the powers of that base until you reach the maximum value that you're going for. There is some other tricks when you're going from like base 2 to base 16 and so forth, if they're powers of the previous base, but we will ignore that. So here I did all this exponentiation. Woo, it's a fancy word. And notice all these values are going to be different. And that's the cool part about actually this process. Because we're doing a mod P and my power 97 is relatively prime to my power, then it's going to give me all different values. So now I just take that and my new cipher message is an array with all of these inside of it. Again, if I'd done blocks and my blocks had been, let's say, blocks of size 4, again, when I did them, they would translate it into an array of each of those blocks in cipher. So that is, we get this new cipher message that's down here. Now we take that, and what we need to do is we need to find E. This is going to let me undo it, mod 180, because we're doing mod P minus 1. So again, remember, I'm going to come back here to this page. E equals 97. I'm just going to write this down so you can kind of see it. Remember, we want D times E mod P minus 1, which would be 180, is congruent to 1. Well, we know E is 97, so it's 97D, which means I'm finding the inverse of 97. Well, how do we do that? What we do is we often use the whole Euclidean algorithm to go through it. And again, using Euclidean algorithm, I find that it's 13. I'm going to skip doing all those steps. If you really have questions about it, let me know on the discussion board. But I think this is why I wanted you all to play with the extended Euclidean algorithm, because we will use it over and over and over again. It is used a lot. So we then find D. The cool part is now that I found D, I don't have to find it every single time. I'm reusing it, so I'm only having to find D one time based on E. And 94, so just for instance, going back, the 94 to the 13th power is actually 4 mod 181, back to my original p-value. I'm going to skip the 1 to the 13th power because I think that's pretty obvious. So 1 and 0 are pretty, they're annoying because then to any power, they're always the same thing. But all the other values work out. And it turns out that when we do larger blocks, it's very rare to have 0 block or 1 block. Especially when we do blocks of size 4 and 5. So as a result, our numbers are typically very mixed up and more confusing. We can repeat this process over and over again for all the rest of our ciphertext, and it turns out it gets our answer. All right, so that is the exponentiation. But the problem with that cipher, real quickly, is the fact that, again, it is asymmetric, which means, I'm just going to come back here, P and E must be kept secret. So how do I translate P and E secretly? Because if they're known, by the way, then D is really easy. If P is known, then, well, I kind of lose, even if P is known, this cipher has, it's wonderful cipher. It's really, really hard to break as long as P and E are unknown. You can, there are some things, but it's essentially trying to do the di discrete logarithm problem, and that's not really easy. Um, Even if P is known, then E must be still at least kept secret. So at least one of them needs to be kept secret for this to really makes the most sense. And P can be known as long as it's super huge. So this gets into the idea of what's called the Diffie-Hellman key. So Hellman, along with Diffie, and again, Hellman himself wrote that technically this should be include Merkle as well. This is based on a paper they published in 1972, if my memory serves me correctly. And they talked about how can we exchange keys in a public space. So here's the idea. Alice and Bob, they've never met, and they want to share a secret key. So again, symmetric, we can do it if we have a secret key, but you have to meet because you have to exchange the key in the first place. So how do we share a secret key over an unsecure channel that other people can see? Quick note, we do use symmetric encryption. Some of you noted this. AES and DES are the most classic versions of symmetric key encryption. DES was actually broken a couple decades ago. It's no longer really used, and AES is the more advanced version of it. Turns out Hellman, by the way, is the person who for a long time told the NSA that DES was bad and they had too short of a key on it, needed a bigger key. So they made a bigger key. That's the idea for AES. So we have to exchange a key, though. Both those are still symmetric ciphers. Means how do we share our key over an unsecured channel? Well, the way we do this is actually based on the discrete logarithm problem. And I'll show you this. So first, Alice and Bob agreed to a prime number. Now notice I want a prime number that's bigger than 2 to the 10,000th power. To the 1,000th power. To the 10,000 is even better. I want something super huge. Now I need to find G, which is a generator of that P. That's pretty easy. Actually, there's a couple different other things. Again, that means something that G to any power will create all the elements mod P, essentially, except 0. And I want G to be relatively big. I want it to have a really large power. So it doesn't have to be the generator of the whole thing, but it has to generate at least most of it and have a large order. The reason being, the larger the order, the harder it is to brute force this. It's a larger set because P and G, I'm just going to tell you right now, are going to be shared. So we're going to share the P and G in public. So everyone's going to know what my P and G are. Wait a minute. So I just created a really, really big prime number, telling everybody about my prime number. I'm telling everyone about my generator. And then this is what we're going to do. So I'm going to go to the next slide because this is really long steps. So Alice is going to pick a random large number n and then compute G to the A mod P. So again, now hopefully A is not bigger than P. It could be just because of the cyclic nature of mod P. It, cycles back in, but you might as well just pick any value that's up to P minus 2. Again, I don't want to pick P minus 1 because any value to the P minus 1 is just going to be, 1. So I pick anything else. So I pick a really large random. What does random mean? That's a whole different question, and I probably should make a slide and talk to y'all a little bit about that. But we make this situation, and I send that to Bob without telling. So I send G to the A. So notice I am sending this to Bob. I am not sending A. All Bob is getting is this big A, which is G to a power. Notice by the discrete logarithm problem, Eve listening in can't, even though she knows G and she knows P, cannot find A because all the possible options are so huge. She'd have to brute force it. All right, so she does this. Bob does a similar thing. He picks a B, little b, and he does the same thing. He raises G to the B. And he sends that to Alice again in public. So now in public, so let me write down real quickly. So what is public and what is private right now? So public, private. Just so you all can keep track of this. Little a and little b are private. So Alice knows A and Bob knows B. And they don't know the other one. So Alice does not know B and Bob does not know A. But in public, we've already shared G, P, big A, and big B, which again, A is G to the A and B is G to the B. So again, these are all public, and because of the discrete logarithm problem, Eve cannot figure out what little a and little b are. But the question is, how do Bob and Alice use this then? Well, it's actually quite simple. I'm gonna have to clear this so I can go on to my next slide. Alice takes B to the A and Bob takes A to the B. Wait a second. This is where the trick comes in. B to the A, remember B was G to the little b. Raising that to the A power is the same thing as G to the A power, all that raised to the B power, which is A to the B. Oh, it turns out that by the powers of exponents and because the commutative property of multiplication, that we now have this shared key. So they have shared everything in public, and yet no one can figure out what K is except by completely brute forcing the discrete logarithm problem. Oh, so this is the key to this whole thing. This is how your book nicely has it all cut out. And I took this picture and posted in here. Again, we choose a large P and a large G. You have to have some kind of trust between who you're sending a message with. Just because you're going to send a message to someone, you probably should know who you're sending a message to. There should be some kind of other stuff, and we'll get to that later on. So this whole idea kind of helps us understand how this works. So let's do an example real quick. Let's let Alice and Bob agree to prime 941 with the generator G is 627. Alice chooses A to be 347. So big A is equal to 390, which is 627, my G, to the 347 mod 941. Now Bob chooses little b to be 681, and big B is now 690. Sorry, little b is 781. Big B is 691, which is 627 to the 781. Again, this exponentiation, real quickly, both of these are done, again, using that fast method of binary expansion, mod 941. You don't actually do 627 to that power and then take that mod. Your computer will hate you, okay? It will absolutely hate you if you try doing this. So instead, we're using that fast exponentiation process of using the binary expansion. This is the critical idea and why we talked about these concepts previously. So this is where we're going to start tying all these ideas together. So because I now have this, now if I am Alice, I send Bob my number 390, the big A. And Bob says Alice 691, which is big B. Both of them can do this over a public channel completely fair. So because we've now shared in public, so let me just highlight what is in public. So I'm gonna make that red. So I have shared my prime number, that is in public. G, that's in public. A, that's in big A, and big B are in public. On the other hand, let me go yellow. Little a of 347 and little b of 781, both of those are kept private. That's the critical concept here. Now we take that and now we don't transmit those. Those have to be kept secret. Now, Alice and Bob both can compute their value. So I can take, so if I'm Alice, real quickly, if I'm Alice, I'm going to take Bob's value of what he sent me. So I'm going to take this 691 and I'm going to raise that to my 347 and it's going to give me 470. And if I'm Bob, I'm going to take the 390 that Alice sent me and I'm going to raise it to my secret key of 781. And it gives me, both situations will give me 470. So that is my shared secret that I can then work on and utilize. So we are going to leverage this to do our encryption. So now we can share our key in public and no one else can know what it is. So let's summarize a couple things about this process. So first, the Diffie-Hellman protocol, K is a shared secret, independent. It's actually generated independently. That means that both of them are creating it without having the full information from the other person. So with only partial information, we're actually creating the same key. This is a cool way to actually transmit information without sharing all of. So we have our own secret key. I don't even have to know what the other person's secret key is, and I still can have a shared key with that person. So that is the really cool part. When this exchange is complete, we now have a secret key that we're in agreement on. And the key thing is this is different than the Polig-Hellman cipher, which both require a P and an E to be kept a P. However, in the Polig-Hellman, I need the P to be kept secret and the E to be kept secret, because otherwise D is easily figured out. If I know both those things, then D is easy and the whole purpose is lost. On the other hand, the Diffie-Hellman protocol, the P and G can be made public because of what's called the intractability of the discrete logarithm problem. Intractability means there's no way to make it simpler than complete full-on brute force. And because of that full-on brute force, in large, big enough numbers, it becomes nigh to impossible to complete. However, there's a subtler problem here, and let's talk about that because we're going to use this. And in fact, it's the basis of a lot of RSA, and you'll understand how it fits in. It's called the Diffie-Hellman problem. So remember, we had the discrete logarithm problem. We're now going to talk about the Diffie-Hellman problem. If I know P and G, the Diffie-Hellman problem is the problem of computing G to the AB if I know G to the A and I know G to B. I don't have to know little a and little b. But if I know G to the AB, and excuse me, if I know G to the A and G to the B, can I figure out what G to the AB is? Now, there's a couple things to point out about this problem. If Eve can solve the discrete logarithm problem, then I guarantee you she can solve the Diffie-Hellman, because if she can solve the discrete logarithm problem, then she can solve G to the A and G to the B, and then all she has to do is G to the product of those two values. However, the question remains, and this is the open question, we don't know if the other way is true. In other words, we don't know if you can solve this, if there's a way to solve this Diffie-Hellman problem without solving the discrete logarithm problem. That has not yet been discovered, and actually is really the kind of the critical key. If there's a way to do this without doing the discrete logarithm problem, then this becomes massively weak. So in general, it's believed, the consensus, that these are the two problems are equivalent. And this happens all the time as this again where there's a lot of different areas of math and computer science, such as P versus NP and so forth. We can argue about different things. But for practical purposes, in the discrete logarithm problem, Diffie-Hellman problem, we consider them the same level of complexity. And so you can't solve one without solving the other. That's how it's pretty much assumed and treated for practical purposes. If you can figure out how to do that, good for you. If you can figure a way to solve the Diffie-Hellman key exchange without discrete logarithm problem, awesome. So I hope that helps get you started and also start to see how we're actually taking all these mathematical concepts of building for a couple weeks. I know some of you are like, why are we doing this? That some of you even posted that Dr. Bailey's messing with your heads. I'm not trying to mess with your head. I'm trying to set you up with the skills that now we leverage to do these things. And again, if you go back on all these examples, they're relatively small compared to the actual prime numbers we picked. Again, I'll go back here. My p-value here was 941. That is nowhere near 2 to the 1,000th power. It is simply a value that I picked to make it relatively small. And so this computation is easy to work with on this example. I'm gonna do the same thing for you. I'm gonna give you relatively small examples. Real world, picking a large prime number is massively hard. That's a whole different discussion point for a different day. But this is why all of this becomes so critical for us to play around with and understand. Good luck. Let me know what questions you have.